everybody. Or no, right now we say ciao, friends. Don't know why, but that's the way of greeting right now from SQL BI. What we're going to talk tonight is about, not tonight, for you is today. So what we're going to talk in this session is about DAX optimization examples. The idea is not to go too deep into optimization techniques, just because we have 1 hour available, which is not enough to go too much deep. But I want you to give you an idea of the kind of performance you should expect from a Power BI report. And we start from scratch. So we start from a report. We know nothing about it, and we will investigate 1 step at a time on the slow measures, trying to find out where the problems are and how to fix them. Now, before I start, very quickly, who I am. I'm Alberto Ferrari. I work with Marco Russo at SQLBI.com. We do a lot of things. These slides are old. We write books, but this is the old version of the book. I didn't update my slides. Anyway, the Definite Guide to DAX, the 2nd edition, is our DAX Bible. It contains everything about the DAX language and how to optimize it. Then we teach courses. We typically do that live, but we can't right now. So if you're interested in learning DAX, attending one of our courses might be an idea. And the content I'm talking about today is included in the Optimizing DAX workshop. We also do consultings. We are BI experts and so on. Anyway, I'm not here to sell myself. I'm here to run you through the answer to the typical question that a new buy or a new colleague might ask you at some point, like, would you mind taking a look at my report? There's something strange. It's slow. I have no idea why, but it will take you no more than a couple of minutes to fix it. And when you hear that sentence, you know that the other person is lying, and a lot of problems are coming out. So what I want to show you is what to do if you are in this scenario and you want to fix the problem. We are not going to say, oh no, I still have the agenda to show. So the agenda is basically understanding that optimization is a set of steps that you need to carry on. It's a technique. It's not art. It's not magic. It's just knowing what you are doing. So in the process of optimizing the report, we will learn how to use tools to measure performance of a report and to understand where the bottlenecks are. Understanding a bit about the way that the DAX engine solves your queries, and understand again the first steps in understanding the formula engine and the storage engine. Keep in mind that whenever you need to optimize something, the first thing that you need to do is being able to reproduce the problem. If you cannot reproduce a performance problem, there is no way you can optimize it, because there is no way to try and reproduce the problem, fix it, and make sure that the problem will not appear again. I don't expect you to say wow at any point during my presentation. This is not marketing. It's a technical presentation. So I want to show you how to do things in a real world. And the results will be kind of amazing, but nothing strange, nothing that you should not expect from your everyday life with a report. So let's start with the first look. I have a report. Right now you see a blank page. That's totally expected, because we want to see what happens when you open the report. And when I click on the first page of this report, you see that it's not fast. To be honest, it's damn slow. You see the images are popping out one at a time. And this is not because it's a remote session. It's actually a very slow report. So just by looking at the report, you have the feeling that something is wrong. These measures are very heavy, and there is some problem. But the thing is, how do you know that where the problem is? We have 1, 2, 3, 4, 5 different visuals in this report, and some are slow, some are not that slow. There is a culprit somewhere between all these visuals, which is wrong, and we need to find who the culprit is. Finding it is not easy, because you cannot just rely on your eyes. So you cannot say, well, probably this is the fastest and this is the slowest, because this is the last that came up. This is actually true, but you cannot rely on it. Moreover, the speed changes because if I click on a slicer, you see that it takes time to refresh everything. You probably don't see a small circle here, but this part is still being updated and it will take a while. But because of the cache in the system, if I remove the filter, it will be very fast. And if I put again the filter, it will be fast again. I need to change the query and go to something different to run the query again and see the speed. So working with the report, and that's the first important lesson, you don't have a way to understand where the problem is because you need to be able to reproduce your scenario. And if you just work with Power BI, there's no way to do that. So what we learned just by looking at the report is that we have 1, 2, 3, 4, 5 visuals. One of them is going to be the slow one, but we have no idea which one is actually the slow one. So the point we reached right now is just this. We have 1, 2, 3, 4, 5 visuals, and we need to find which one is the slowest one. How do I discover that? Well, I can start investigating a bit over the problem. At this point is where I typically ask the audience to tell me what they want to do. Doing that online is not very effective because I don't see the chat. I don't see what your answer would be. So I will just guess what you probably would say and go ahead. We can start investigating on the model. Well, the model is kind of simple. It's a star schema. So we have orders. Orders is our main table that contains orders. Orders placed to customers. Let me zoom in a bit. Customers. So an order is placed to a customer in a specific date. And then we also have exchange rates. The reason is all the orders are stored in US dollar, and we want to show the values using two different currencies. If you look at the report, you see that we have the amount in US dollars and the amount in euro. The conversion happens on the fly. So that's why we have an exchange rate table that tells me the exchange rate at the end of every month. From the size point of view, this model is not very large. The orders table is the largest one, and it only contains 1.6 million rows. Now, 1.6 million rows is tiny. You should expect milliseconds to answer any kind of query from such a table. Nevertheless, it is slow. And if we go a bit further, we see that we have the amount in USD, as we said, the amount in euro. So we know that some kind of currency conversion is happening here, and that might be an issue. And then we have this measure, open orders. Open orders tell me how many orders are open at any given point in time. An order is open in the time between when the order was placed and when the order was delivered. In between those two dates, an order is considered to be open. So year by year, how many orders we had open, meaning that they started at some point in 2009 and they were not yet finished in 2009, or they were being handled in 2009. So we have three measures, the amount in USD, the amount in euro, and the open orders, several visuals, and we don't know where the problem is still. We can take a look at the measures. So we can take a look, for example, at amount USD. Let me zoom it a bit, or open orders, or amount in USD, just amount in euro. You see that amount in euro has a lot of code, but we still don't know where the problem is. So the first and most important lesson to learn is to measure. Whenever you have a problem, whenever you want to understand where a problem is, you need to measure it. You need to understand it better. Power BI offers you a tool to do measuring. If you go in the View menu, you have the Performance Analyzer. Performance Analyzer is a great tool, even though the kind of results it produces are not easy to read. If you enable Performance Analyzer, this panel opens the Performance Analyzer. You can start recording, and since at the moment when you start recording, every time a query is sent to the server, it is being measured in terms of speed. Now, if I click on bachelors, you see that the query is being executed. And here you see some numbers. It shows all of the visuals, open orders by education, open orders amount, slicer, open orders by continent and year. And for each one, we have the duration in milliseconds. I click on it again, it will compute it again. But actually, the best thing that you can do with this is to clear everything and then refresh the visuals. If you refresh the visuals, all the visuals in your report will be completely refreshed, and the engine is measuring the time needed to execute everything. It will take around 10 seconds to execute everything. Now you have the duration in milliseconds, and for each visual, you have basically the duration. One of the nice things is that if you click on a visual, it is being highlighted in the report. You see that if I click on slicer, the slicer is selected. If I click on open orders, this visual is being highlighted. So I have a clear way of understanding what I'm clicking on to. Now we have numbers here. 127 milliseconds to refresh these open orders, 11 seconds to refresh this visual, which is the chart, 143 milliseconds for the slicer. These numbers are nice, but the first thing that you need to learn about the performance analyzer is that this number have a very clear meaning, which is nothing at all. They don't have any real meaning. Because this is not the time that the engine needed to execute the query. This is the time that the engine needed in order to produce the visual. And it is made up of 3 different numbers, which are the time to execute the DAX query, the time to visualize the chart, the time to prepare the visual, and other. Other is my favorite because it means nothing. Other is just a number, a time that is needed in order to do other things. In the case of Power BI, those other things is waiting for other visuals. In this report, we only have 5 visuals, so other will be small nearly everywhere. But if you have 100 or 200 visuals in a single report, other will be the time that the engine had to wait for other visual to finish before starting the current visual. And it is not uncommon that under other, you have the largest amount of time. So you might see a visual that takes 10 seconds to run. Out of 10 seconds, 9 seconds are in other, and only half a second is on the DAX query. Why do I mean that this number is meaningless? Because no matter how much you optimize the query of that visual, you will never reduce the time for other. The only way to reduce other is to reduce the number of visuals. In our specific scenario, this is not a big problem because having a small number of visuals, other accounts for not too many values. So we have 5 visuals. Let's analyze them one by one. The slicer takes only 2 milliseconds to run, so it's not even worth our time. Then we have open orders by continent and year, 2 seconds. Out of 2 seconds, actually 2 seconds is spent on the DAX query. And this is this visual that is showing the open orders sliced by continent and by year. So it looks like open orders is not our biggest problem. Then we have sales by year in USD and Euro. Sales by year in USD and Euro, here it is, takes 2.4 seconds to execute. And then the worst one is open orders amount USD and Euro. This chart, this is going to take a lot of time to run. It's 11 seconds. And this report contains both the open orders and amount in USD and amount in Euro. So if we want to optimize the code, we know the problem is somewhere in these 3 measures, and it's likely grabbing the query which executes this report is our best chance of reproducing the problem. If I want to find the query that runs here, what I need to do is just go here under this part and just click on copy query. This copies the query on the clipboard. So Now, in my clipboard, I have the full query which fills this report. How do I run the query and measure performance? Well, I cannot do that from inside Power BI. I need to use DAX Studio to do that. So I need to launch DAX Studio, connect it to my Power BI file. And then from here, I only need to pass the query. And you see that the query is just a top n 1000 of a summarized column, that summarizes by year, month, and month number and computes the three measures. Part of the query is totally useless. The top n 1001 is useless. You will always see a top n every time you see a query run by Power BI because it never grabs the entire set of values, but only the top 1000 or top 500 or top whatever. And so the order by, we're not interested in the result, we're more interested in the timings. If I run the query now, it will take 10 seconds to run. And you can easily say it's going to take 10 seconds by looking at this number, which will grow up to 10 seconds up to the end. And then I can also see the results. I'm not interested at all in the result. I'm only interested in the time. The problem is that this time is not very precise, and it does not give me very clean information about the real time needed to execute the query. So when you need to optimize your code, what you need to do is enable the server timings. Here in performance, you have query plan and server timings. We're mainly interested in these two buttons. The query plan is sometimes useful, but it's really, really deep in the way the engine works. The server timings gives you a precise measurement of how long it takes to run a query. You need to wait a while until you see this new panel coming out, server timings, which right now is not showing anything. I need to run again the query to measure it. Keep in mind, if I run the query now, I will get some numbers, but I will not get the correct one because there is a cache in analysis services, which is the engine running in Power Pivot, that is caching partial results. So if I want to make sure that I get always the correct numbers to improve performance, I always need to clear the cache before running a command. There is a button here in DAX Studio that clears the cache of Power BI. And that's an option, or where I have the run button, I can choose to simply run the query, or, which is much better, clear the cache every time and then run the query. So I can simply click on run. This will clear the cache first and then run the query. Let's do it now. So we see what happens in the performance pane. Right now it's running the query. We know it's going to take around 10 seconds. And at the end, we will have the correct numbers. We will have the total execution time, the storage engine time, formula engine, and storage engine. For now, what we are interested in is only 11.9 seconds. So this is the time we need to beat. Then all the other numbers, we will go to them a bit later, as we will try to understand what are all these strange queries that appears everywhere. Now, we know it takes 11 seconds to run a query that contains 3 measures, but out of the 3 measures, what is the relative time of each of the measures? We have open orders, amount in USD, and amount in euro. I want to measure the 3 measures separately. So we can start just commenting out one by one. I can run amount in USD, and the amount in USD runs in 10 milliseconds. So this is clearly not the culprit. We can get rid of amount in USD because there is nothing interesting to see there. Let's take a look at open orders. Open orders will take a bit longer. I have honestly no idea how long it will take, around 7-8 seconds, I guess. A bit more, 9.5 seconds is the time spent to compute the open orders. What about in euro? If I run it, this is going to take a bit less. It was 10 seconds before, it's 2.3 seconds. So we have 3 measures, and we know that this is around 9.5 seconds. This is about 2.4 seconds. What I should do at this point is focus my effort on the slowest one, open orders. Nevertheless, we are not going to start from open orders because that's a bit harder. We start from amount in euro. Now, how do I fix it? I have two options of fixing it. The first one is, well, first I need to understand what this measure computes, and then I will need to change the measure one step at a time until I fix the DAX code and make it work in a better way. How do I change the measure? One option is to go here, click on amount in euro, click on amount in euro, look at the code, and then start to fix it. But this requires me to jump back and forth between Power BI and DAX Studio to do the changes to the DAX code and then the measurements in DAX Studio. There is another more interesting way of obtaining the same goal, which is define the measure local to the query. If I search here in the metadata panel of DAX Studio, if I click under orders, you see that I have amount in euro. I can click here, then right-click on amount in euro, and I have the find measures. If I click on the find measures, look what happens. The full code of the measure is copied in my query with the same name and the same definition that I have in Power BI. What is the advantage of having the definition here? If I run this query now, the engine will not use the original definition of amount in euro. Instead, it will use this definition. So I can do any change here, and the engine will use this definition. We can easily check it. If I define the measure as being just 1 and I run it, you see that it's obviously very fast, and the result is 1 everywhere. So whatever change I make to my code here will be reflected immediately in my query. And that's the easiest way to reproduce the things again and again. Another thing which is important is that the measure amounts in euro uses amount in USD. And I'm not sure whether the problem is in the code here, or maybe is in amount in USD. Amount in USD is another measure. So my measure calls another measure, and the problem might be in my measure, in my first measure, or in the inner one. What if I want to see also amount in USD? There's an easy way of doing it, which is not using the find measure, but the find dependent measure. If I click on the find dependent measure, DAX Studio will not add only the current measure, but it will also add all the measures that are used by amount in euro. So because amount in euro uses amount in USD, I also have the definition of amount in USD here. And again, whatever change I do to the two measures will be reflected in this query immediately. With that said, it's now time to start diving a bit more in the DAX code and understand where the problem might be. This requires a bit of analysis of the code. Amount in USD is super simple. There's nothing that should surprise us here. It's just a sum of a column. Amount in euro does a conversion on the fly of the value in USD into value in dollar. And how does it do it? It iterates over the orders. For each order, it computes the amount in USD, and then it multiplies the value for this giant expression. Now, despite being very long, this expression is kind of simple because it first checks if the average rate at the date, which is the first of the month of the current order and the year of the current order. So it's searching for the first day of the month, where the currency is the currency key, where the code is euro. So it's searching for the currency key of euro on the first day of the month, and then it computes the average rate. Average rate is in the exchange rates, which contains the rate, the date, and the currency. So this lookup value is basically retrieving the exchange rate on the first day of the month where the order was placed. The reason why it uses the first day of the month is because in this specific data model, we don't have exchange rates for every day. We always have the exchange rates at the beginning of the month. So all the orders in a month will use the exchange rate of the first of the month. And because of data quality, that exchange rate might be missing for whatever reason. What happens if we don't find a value? So if this expression returns a blank, it means that we do not have an exchange rate. Therefore, we compute the average exchange rate of euro over all time, and we use that average to do the conversion. Otherwise, if we found a value, then we use that value. So the amount in USD of that specific order is multiplied by the exchange rate on the first of the month, or the average of all exchange rates, depending on whether we have the data or not. As I said, despite being somewhat convoluted, this code makes sense. It's only long, but that's the only problem of this piece of code. Where do we start optimizing it? We have a lot of options, but whenever I ask it in classroom, one of the first things that we notice is that we are doing a lookup value to search for an exchange rate, and then we are doing the same lookup value again to compute the same exchange rate. And this is not very smart. We are doing twice the same operation. So let me run the query again because I want to have a base measurements. This query runs in 2.3 seconds. So let's start modifying it. I can take this entire lookup value and store it into a variable. Define a variable exchange rate where I put my lookup value. We add the return, and here we say if is blank the exchange rate, then do that calculation. Otherwise, just use the exchange rate. And let me show you one of the best features of DAX Studio. You see that the code is now messed up, but DAX Studio is integrated with DAX Formatter, so you can click on Format Query, and the query is formatted on the fly while you modify it. So that makes it super easy to always have the code the right way. So I created a variable. I avoid doing the calculation twice. We start from 2.3 seconds. If I run the query again, I expect it to be a bit faster, but not so much faster. We saved 300 milliseconds out of the query, which is not bad, but it's not still fast. We can notice another thing. Look at this calculator. This calculator is computed the average exchange rate over all time of the currency we are using, which are US dollar against euro. Now, this number never changes. It is always the same. So there is no need to compute it here. I can compute it outside of the entire iteration. Define a variable here, exchange rate all time, where I compute my number. And then here I can use exchange rate time. Let me format it again. There is a problem somewhere. I'm missing a return statement. So now I compute outside of the iteration, I compute the exchange rate over all time, and I use it here. Inside the iteration, I compute this lookup value, and I use the value here only once. Again, we start from 2 seconds, putting the code of exchange rate all time outside, goes from 2 seconds to 2 seconds. 1978 is still very large. So this doesn't save anything specifically. What else can I do? What can I do to make this code be faster? Well, to make it faster, what I need to do is dive a bit more into the execution, into the query plan. Whenever you run a query in DAX, there are actually two engines which are running. One is the storage engine, the other one is the formula engine. Storage engine is responsible of gathering values from the database. Formula engine computes values on top of it. Storage engine is extremely fast. Formula engine is extremely slow. And if I look at these numbers, I see a bit more information. I see that it takes 2 seconds to run the query. 1.5 seconds are spent in storage engine. Half a second is spent in formula engine. And this bar shows that 23% of my time is spent in formula engine and 77% of my time, on the other hand, is spent in storage engine. And these are the queries executed by the two engines. You see that I have two queries that retrieve a lot of columns, the quantity, the customer key, the order number, the sales amount, the order date, the delivery date, and this is retrieving 1.6 million rows, meaning that the storage engine needs to retrieve 1.6 million rows, pass them to formula engine, and then formula engine will do some sort of calculation. 1.6 million rows is not a random number. Is exactly the number of rows in my orders table. If you look at the orders table, it contains exactly 1.6 million rows. So this query right now is materializing, is building an in-memory data structure that contains the entire orders table. Why does it need it? The reason is this call to amount in USD. This query is iterating over orders. For each order is calling amount in USD. Amount in USD is a measure defined here that computes the sum of orders amount. Because of context transition, here you have some sort of calculate around it, calculator which always appear before any measure performs context transition, and context transition forces this calculation to happen only for the current row. Context transition is fine, it works, but it's a slow operation. It's not very fast. You can rely on context transition if you need to do a small number of iteration, but if you need to do millions of iteration and still rely on context transition, your measure will be slow. Besides, look at what I'm doing here. I'm calling amount in USD, and amount in USD is just summing orders amount, the amount column in the orders table. Now, what is the sum of orders amount for a table that, because of context transition, will contain only one row? Well, the sum of amount for one row is just the amount. So the best way to optimize this code is to take this order amount here instead of amount in USD and just rely on the row context, avoiding calling a measure from inside an iteration that happens for millions of times. Doing this small change, now I no longer need the definition of that measure because I no longer use amount in UR. And look what happens. We go from 1.9 seconds to much better execution time, which is 230 milliseconds. That is 10 times faster. Most of the time is spent in storage engine, and the value for formula engine are still, it's still there, but it's reduced. So the overall query will run much faster. So we moved from 2.4 seconds to 200 milliseconds, around 12 times faster. But we can still do a bit better than that. Because think of that, we are iterating over orders. For each order, we compute the exchange rate on that data, and then we compute the amount, and we check this is blank. So how many iterations will the SumX function do? It will do 1.6 million iterations. Lookup value will be called 1.6 million times, and this if statement will be executed 1.6 million times. Both operations are faster, but if you execute them a lot of time, of course, you you reduce the speed of your query. And the question is, how can we improve that? How can we reduce the number of iterations executed by my iterator? Actually, if you think a bit about it, do I really need to iterate this code order by order, line by line on my order table? Because we know that we have the exchange rate, and we know it because of this lookup value, that changes only once per month, we can go for a different algorithm. We first compute the sales amount month by month. We compute the exchange rate month by month, and then we multiply them one by one. If I have a year of data and I group it by month, instead of 1.6 million rows, I will have 12 rows. So it will be 100 times smaller. Therefore, it makes a lot of sense to group earlier by by date. So what I can do is instead of iterating by order, I can summarize orders, and I do that by date, year, and month. Year and month is a column that contains the year and the month together. So this is going to return only 12 rows for the year. And then I add a column to all these, which I call amount, which is the value of amount in USD. Let's call it amount in USD. You see that I'm going back to calling the measure, which is not bad in this case, because I'm calling the measure only for 12 times. I'm no longer calling the measure for 16 million times. So now I have these add columns returns the year amount and amount in USD. I also need the 1st of January, the 1st of the month. So let me retrieve last date in month, which is just a calculate max of date. This is needed to have a date that I'm going to use here to compute the 1st of the month. So I have last date in month here, and I use it here. I take the year of last date in month, the month of last date in month. I'm doing only damages here. Let me copy this. And then I still do my lookup value, obtaining the euro. And then I compute no longer orders amount, but amount in USD. Multiply by, if it's blank, exchange rate, and exchange rate all time, otherwise exchange rate. And that's it. By doing these add columns, I have now reduced from 1.6 million times the number of iterations to only 12 or 24 or 12 times the number of years rows in my report. Again, we have a baseline of 213 milliseconds, and if I run it again, I have an error, of course. Amount in USD has not been found. Why? Because I mismatched it. That's at amount in USD. Okay. It was 200 milliseconds, and now it's 33 milliseconds. Again, 10 times faster than my best option. But if you do the complete math, we move from 2.4 seconds to 33 milliseconds, which is kind of awesome, just by fixing the DAX code and understanding where we wanted to do the correction. Last thing that I need to do is copy this code. I'm just copying it to the clipboard. I can go to Power BI. And this last step, I need to do that by hand. So I need to go here, get rid of everything, and copy the code that I wrote. And this will reduce the execution time of everything, but I still have to optimize the open orders. I told you earlier, how do I compute the open orders? Open orders is computed by checking how many orders in a given day are open. And an order is considered open in between the order date and the delivery date. Let's take a quick look at our data set. The orders table has two columns, the order date and the delivery date. This is the 8th of October up to the 18th of October. So any date between the 8th and the 18th, the order need to be considered open. After the 18th is closed, before the 8th, before the 8th of October, it is non-existent. It's not there. So the open orders measure, the open orders measure is much simpler actually than the previous one. Given a period in time, open orders takes the minimum date, the maximum date, and then it computes, it filters the orders where the order date is before the end and the delivery date is after the start. Why do we need end period and start period? Because if you have one day, it's only one day, it's very easy to understand whether an order is open or closed. But if you have multiple dates in the selection, it's no longer so easy to understand it. I don't remember if I have a slide that explains that. Let me see. As you're going to learn, I never follow those slides. I do everything on the fly. Yeah. Think of that. If I have one day, it's very easy to understand whether an order is open or closed. But if I have a period like October, I know that order 1 is not open. But what about order 2? Order 2 was not open at the beginning. It is not closed. It is closed at the end, but it was open at some point in October. Do I want to count it as open or not? That's a choice you need to make. In the version I wrote, I consider order 2 in October as being open. The same for order 3. It was not open at the beginning, but it was open before the end, not closed, so I consider it open. Order 4, of course, it's neither open nor closed because it started after the end. And order 5, it was started and closed in October. And again, the question is, should I consider it open or not? In my algorithm, I consider it open. So I want the result to be 3. In order to compute 3, I want all the orders that were not ended before the beginning of the period and were started before the end. This will include order 2, 3, and 5, and skip 4 and 1. And this is reflected in the code I wrote. I'm returning all the orders that were ended before the end, no, that were ordered before the end, and ended after the start. This produces the result. I need to use this old data to get rid of the effect of the relationship that I want to kill before doing the math. The problem is that this measure is damn slow. Let me repeat the process I did earlier. I remove everything from here. Now I'm focusing on open orders. So let me uncomment and put this again. I still know that it takes 9.5 seconds to run it, so I can save those time and avoid executing it. And I can define the measure, the open order measure here, so that I can change the measure and see the effect of my changes. There's no need to run it. Well, let's do it. If I run this query, I know it will take 10 seconds, but the real question is, how do I optimize this code? It's utterly simple. There's not much that seems to be needed in order to optimize it. Actually, there is a lot of work that we can do here. And even though it's very, very simple to do, understanding the reason is kind of tricky. What this code is doing, is asking is to count the number of orders where the orders are in between the order date and the delivery, where the date is less than the end period and the delivery date is greater than the start period. Again, to materialize the entire order table. And you can see that from the number of rows which are returned by this query, it's still 1.6 million rows. And it's retrieving for 1.6 million rows the order date and the delivery date. Generating a table with 1.6 million rows and scanning it takes time. There are multiple ways of optimizing this query. The easiest one is to split the condition, because the condition involves order date and delivery date. But you can write the very same expression, instead of using filter, using calculate, separating the two filters, one on order date and one on delivery date. You should remember, always remember, that Tabular is a columnar database. Being a columnar database means that operations executed on one column only are much faster than operations that involve managing multiple columns. So how can I write it in a way that it works on column by column? I can rewrite it saying, hey, give me the count rows of orders. Where order date is less than delivery date and order date is greater than start period. For all date. I just rewrote the expression using calculate, counting the orders. I removed filters, so I removed the iteration from my expression, and that's the most important thing. I split the two conditions, one on order date and one on delivery date. This change, as small as it is, moves the entire query from 11 milliseconds to 74 milliseconds, which is kind of awesome because it generates a much better query. Again, what I need to do is take this entire piece of code, go here, replace my query. And at this point, the result is pretty nice. With these two changes to my measures, you see that now I can click on any filter here, change clerical manage manual. And this is the kind of performance that I would expect from Power BI. If I was Christian Wade, I would probably say that's a clicky, draggy, droppy experience. But I just call it the normal experience of browsing a data model. There's one last thing that I want to show you. I still have 10 minutes, yeah, which is how to go a bit farther with the optimization. Because look at the execution time of this query. This query takes 74 milliseconds. 31 milliseconds are storage engine CPU, and 41 milliseconds are formula engine CPU. One important thing about storage engine and formula engine is that the storage engine time is cached. So whatever happens in storage engine is being kept in a cache by the engine, and the engine will reuse the cache among multiple queries. Whatever happens in formula engine will need to be executed again and again. So if I run this query once more, I run it once. No, I need to get rid of clear cache, sorry. Let me move to just run query. If I run the query once, it took 77 milliseconds. If I run the query a second time, you see that the storage engine CPU now is 0, and 39 milliseconds is the formula engine time. If I run this query again and again and again, it will always take around 30, 40 milliseconds. It's 41 milliseconds. If I run it again, it will be around 40 milliseconds. So I cannot save storage. I cannot save formula engine CPU. I can only save storage engine CPU between different queries. The reason is that this code is still a bit tricky. If I want to super optimize this model, what I need to do is go one step further. Going one step further requires changing the algorithm. To change the algorithm, I need to change the data model and move from this model to this model. Instead of having the order structure in this way, I can change the data model and create one row per day of order. So I create one row for every day where the order is open. Doing that, I will move the complexity of the calculation in a calculated table, and computing the number of open orders will be just a matter of counting these two rows, because this is October 1st. In October 1st, I have only one row, one value here. For October 2nd, because both this order and this order are open, I will have two rows. So what I need to do is generate a table that contains one row for every date where the order is open. How to do that? Well, what I need to do is, again, ask help to DAX Studio. I need to create a table that uses generate. I use a generate over orders of dates between from the date between orders order date and orders delivery date. This query, it's going to take a while to run because it contains 16 million rows, but it's going to return all of for each order, all the dates between the order date and the delivery date. Out of the entire query, I just fixed the code while we are waiting for it to finish. I'm only interested in having the orders order number, and then I want the orders customer key, and I want the date. It's actually taking a bit more than what I was expecting. Select column. Oh, I need name, order number, and then customer key, and then date. So this query, okay, returns. No, it's still not returning. We don't mind. This query returns the order number, the customer key, and the date. We will see the result in Power BI where it's a bit faster. So I can go here, create a new calculated table, modeling, new table. Let me cancel the query. Hopefully this will start. Now it looks like I have been able to crash Power BI. That's beautiful. No, that took a lot of time. I can create the open orders table. Open orders now is generating my table with 16 million rows. This table is much larger than the original one. The first table is 1.6 million rows. This contains one row for each day when the order is open. So depending on how long the order stays open, this will contain a multiple of the rows. On average, Contoso keeps an order open for around 10 days. So my open orders, the content of my open orders table contains the order number, the customer key, and the date. And I have one row per every day where the order is open. If I sort it by order number, you see that this order has several dates, one for each day when it is open. Once I have my table, I can only need to build a couple of relationships, like the relationship between customer key and customer. between customer key and customer, okay, and between order number and order number. Okay, that's for sure a bug. Order number and order number. No, it doesn't like it. Oh yeah, that is not expected to work. Sorry, my bad. I want to build a relationship with data and the relationship with customer. I didn't want to build a relationship with orders. I want to build a relationship with the customer and data. Orders is here, and this is another fact table. Once I have these open orders, how can I count the number of orders which are open? That's just a distant count of the order number. So I can control Z while. I want the original query I had before this evaluate. Okay. And now I can replace my measure with just a distant count over open orders. Let me run this query again so we have a baseline. We start from 41 milliseconds. And as you are going to see, this is not going to be much faster. Probably it's going to be a bit slower than this one. But I would expect the distribution between storage engine and formula engine to be in favor of storage engine. So if I run a distant count of open orders, order number. I hope I wrote it right. Open orders, order number, yep. Being a simple distant count should be much faster. Not much faster, but should favor formula engine. Let me see what happens. It's actually slower. It takes 233 milliseconds. But what I'm interested into in this case, it's 7 milliseconds is spent in formula engine and 226 milliseconds is spent in storage engine. The good thing about writing the code in this way is that if I don't clear the cache and if I run it multiple times, you see that now the execution time is 1 to 2 milliseconds. Why? Because it is in cache. It is not recomputed again. It's just using the value that was in cache, which is available if you spend most of your time in storage engine. This feature is not available if most of your time is spent in formula engine. In a multi-user environment with thousands or hundreds of thousands of users, using the cache the right way makes a really huge difference between code written the right way and written the wrong one. So let's go for a conclusion. I used all of my time. If you want to do optimization, well, you need to understand, of course, the basic of optimizations. That's in the book, in the courses we teach. You need to learn the details. And then the steps you need to do is first download and install DAX Studio, spend time learning how to use it, and then prepare to measure, test, update, and then loop back, measure, test, and loop back, measure, test, and loop back multiple times. DAX Studio is your best friend. Optimize is just a complex process, but it's also fascinating. It's beautiful to see how small changes in your code actually have a strong impact on the performance of your model. Now I think I ate all of my time. If you have any questions, just ask. If you have them later, just send an email and I will be happy to answer at any point.